Hi, class. So today we needed to finish up our lab on the calibration. So this is a wrap-up video. We need to kind of understand what we did. So let's review that. So the first thing that we did was we took a culture of E. coli stock tube, and we did some serial dilution. So we first did a serial dilution, um, taking 1 milliliter and putting it with 9 milliliters of saline, 1 milliliter bacteria solution into saline. And so that was a 10 to the minus 1 dilution. And then we did a 10 to the minus 2. So we took 1 milliliter of the 10 to the minus 1 and diluted it to 10 minus 2, all the way up to 10 to the minus 8. Okay, and so that was one serial dilution. And then we plated those. We did spread plates. And then later on, we countered them. And so we took the 10 to the minus 6 plate, and that was a total of 122 colony forming units. So what we have is a calculation. So to figure out the CFUs per milliliter, we take the CFUs from the plate, number counted, times 1 over the dilution factor, times 1 over the volume plated. Okay, so the CFUs per milliliter is going to be equal to the plate that we chose, which would be 122, and then it's going to be times 1 over, it was a 10 to the minus 6 plate. And then we took a tenth of a milliliter, which is 10 to the minus 1 milliliters, is the volume plated. Well, whenever you have exponents that are being negative in the bottom part of the equation, we can move them to top as a plus. So we can rewrite this as 122 times 10 to the 6 times 10 to the 1. And then when we're multiplying exponents, we just add them. So this is going to be combined to be 10 to the 7th. Okay, so 122 times 10 to the 6th times 10 to the 1 is equal to 122 times 10 to the 7th. Okay, so 122 times 10 to the 7th CFUs per milliliter from that equation. All right, so normally we might consider putting this in standard scientific notation, scientific notation by moving the decimal until we get a number between 1 and 9, so it would be something like this. And so it'd be 1.22 times 10 to the 9th CFUs per mil. But we're going to keep this at 122 times 10 to the 7th CFUs per mil, and we'll show you why here in a moment. Okay, so we have a graph here. I'm going to switch screens to a new share. So this is our results. So in the other tube that we did, we took our sample and then we did 1/2 dilutions. And so this is that tube, and we ran it onto the spectrophotometer. So we did a 1x tube, our full strength was 1.13 absorbance. And then 1/2 dilution, so we took half of that. Basically 5 milliliters of the stock, and then added 5 milliliters of saline. That's a half dilution of 0.75. And so that's kind of what we did. And these are the numbers that we came up with from our spectrophotometer. Okay, and then what I did is I created a graph. Here's the dilutions down here. And then up here is the absorbance at 600 nanometers. Right, and then you get these data points, and then the computer in Excel spreadsheet program just connects the dots. Well, that's not really what we want. We want a best fit straight line. So I had the computer generate that best fit straight line, and then it's this dashed line right here, okay? And that's what we'll use. Okay, so what it's telling us is that if we have a absorbance of a 0.6, it's going to come across this line and hit the dotted best fit line and then come straight down. And then we would have the equivalent of a 1/4 dilution of our sample. Well, that doesn't mean anything to us. So we needed to get the numbers put in. And so we figured out that we had 122 times 10 to the 7th. So we have 122 times 10 to the 7th CFUs per milliliter was the full strength stock, okay? And so that would be up here is 122 times 10 to the 7th. And then half of that would be the half dilution. So we dilute it in half, so we expect half the number of cells. So that'd be 61 times 10 to the 7th, and then 30.5, and on, okay? So now we can take and redo our graph, and we put the 122 is right here, and then 61 is right there, and this is all multiplied times 10 to the 7th CFUs per milliliter. 1/4 is 30.5, and 1/8 is 15.25, and 1/16 is 7.625, and 1/32 is 3.8125. Okay, and so now we have some real numbers. And so now if we have a sample of a tube of bacteria that we don't know the concentration, we don't have to go through the serial dilution multi-step process. We just have to put it in the spectrophotometer, and if it reads out a 0.6 for absorbance, we run straight across until we hit the dotted line, the best fit line, and then we come straight down, and it's just shy of 30.5 times 10 to the 7th CFUs. So if we have this dilution, or this original cell culture that we don't know what the CFUs per milliliter is, we can just stick it in there, and then in this case, if it was absorbance of 0.60, then we would have 30 times 0.5 times 10 to the 7th CFUs per milliliter. If we had an absorbance of 30, it would be right in here. We would just come across, hit the line, and then be about 15.25. And then we have to extrapolate. That might be, maybe a 12. So that would be a best guess would be a 12 times 10 to the 7th CFUs per milliliter. And that's how we do it. And it's pretty straightforward once you have this graph. So now in the future experiments, we're just going to refer to this graph, and then we'll take it and find the absorbance that we're looking for, and we'll put it on our graph, and then we'll come across, hit the dotted line, come straight down, and now we have this number of CFUs per mil. So it's a really slick way to quickly figure out the concentration. So you can use this to see if something has grown very well. So we'll be doing different temperatures of growth. So we'll be able to compare, how well a sample grew at, say, 20 degrees Celsius versus 37 degrees Celsius, because we'll have real numbers, because all we have to do is take the absorbance and put it in spectrophotometer, put the sample in absorbance in spectrophotometer, and then come out with the CFUs per mil based on this chart. Now, we just have to recall that we said that this chart only worked for E. coli, because that's what we built this chart around, was the E. coli. If you use something like a Micrococcus luteus or a Bacillus subtilis, then you have to repeat the whole experiment with the dilution for the 1/2 dilutions for the spectrophotometer, and then 1/10 serial dilutions for the spread plating, you have to do all that again and create your graph. And then once you're done, then you can use it all the time for that bacteria. So it's really, really good if you're using the same bacteria over and over. And that is the wrap up for this lab. And if you have questions, ask Christy, and or you can always email me. But ask Christy first and then go from there. All right, I think that's it.